Okay, this is 5-4 of geometry. So a median of a triangle is a segment whose endpoints are a vertex. So up here is the vertex, right? And the midpoint of the opposite side. So here's our midpoint. So that is a median. So medians are also concurrent. And what they are, how they work, they don't just have pieces congruent. What they have, though, is that the point of concurrency, which is called the centroid of the triangle, splits each of these segments into thirds. So like that, 1/3, 2/3, 3/3. So one side is 2/3 of it, and one side is 1/3 of it. So we have these little equations here we can use. That DC is 2/3 of DJ, the whole thing. I just think of it usually, instead of trying to memorize exactly how I'm supposed to multiply it, I just draw it out and picture it as thirds. So the centroid of the triangle is where the medians meet up. So, finding the length of a median. So, let's look at their problem first. It says, in the diagram at right, XA is 8. So remember, you can picture this as thirds. Let me draw it out. Split it up into thirds. So, there and there. And I know this whole piece here is 8. So then what does that make 1/3? Right? I've got 2/3. So if I split it in half, this must be 4 and this must be 4. And since these are thirds, this one also must be 4. You could also use the equation like they do here, that XA is equal to 2/3 of XB. So let's try another one on our own down here. So it says in the diagram, ZA is equal to 9. ZA, let me highlight it again. This is my whole segment I'm looking at. Split it into thirds. ZA, this whole bit, is 9. So, and they want to know what is the length of ZC, the whole thing. So, if this is 9, each of these is 4.5, right? So this one is also 4.5. So then ZC is 4.5 plus 4.5 plus 4.5, which is 9 plus 4.5, which is 13.5. Right, and down here we have AC would be 4.5 if we were asked to find that. Okay, an altitude of a triangle is the perpendicular segment from a vertex of the triangle to the line containing the opposite side. So what that means is, if I take this perpendicular, this altitude is if I take from this vertex up here and I go perpendicular to the line. That would be an altitude, excuse me. It looks a little bit different in different triangles. If I have an obtuse triangle, this altitude is going to go out to the extended line down there. That would be my altitude, at least for this specific vertex. Right? Because this one's going to go like that. And when we're working with right triangles, so the altitude that goes from this vertex is just going to be this whole side, because that's perpendicular. So it could just be the side that's already on the triangle. Okay, identifying medians and altitudes. Let's just look down at our problem. Okay, identify either as a median, an altitude, or neither. So AD right there, goes from a vertex to a midpoint, right? It's marked as being congruent. So that's a midpoint. So that then is a median. It goes from a vertex to the midpoint. EG goes from the midpoint just to the other side. That's not anything. That's neither. And CF. So it goes from a vertex and it's perpendicular to the other side. So that is an altitude. We have concurrency theorem for altitudes. So altitudes are concurrent. They all meet up at one point. And we call that point the orthocenter of the triangle. So again, you can see this is another one where when it's an acute triangle, the orthocenter is inside. When it's a right triangle, the orthocenter is always the vertex with the right angle. Always. This will always be the orthocenter in a right triangle. And in an obtuse, the orthocenter is outside of the triangle. Okay, so we can graph and find the orthocenter. Let's try our problem. So I'm going to graph these vertices. D, E, and F. I'm sketching my triangle here. You can see this is a right triangle. Where did I say the orthocenter is always located in a right triangle? Always at that vertex where the right angle is. So our orthocenter is at 1, 2. If I were looking at a triangle something like this, remember my orthocenter, and let me draw my altitudes over here, right? It goes from a vertex perpendicular to the opposite side. So there's one of mine. Here's another one. So it goes from the vertex perpendicular to the opposite side, right? And that's why this is where my orthocenter is, and I'll sketch in the third one just so you can see it, but it would go from the vertex perpendicular to the opposite side, so something like that. So whereas these meet up at the corner, this one isn't going to. So what I would need to do if I was going to calculate this and not just rough sketch it in, is I would need to figure out the slope of this line, and then I would need to take that fraction and flip it and change the sign so I could figure out the perpendicular slope, and I would need to go through this vertex over here. So I would make this perpendicular, right, and that continues on, and from this one in perpendicular, from this one in perpendicular, and you can see with my rough sketch that right here is our orthocenter. Here's a nice summary of the different names for all those concurrent points, or points of concurrency. We've had quite a few different terms, so this is a great summary. And there's your homework.